All right, in order to prevent our last video from being really long, I split it into two parts. The second part of the video is just going to be a continuation of redox reactions, and we'll try to get some more practice under our belts too. But I wanted to introduce some new terminology. And the first term I wanted to introduce is called an oxidizing agent. And an oxidizing agent is kind of a confusing term, but let's try to break it down into its parts. The first part is really easy to remember. An oxidizing agent is a reactant that oxidizes another reactant. So that's pretty easy to remember, right? And if you think about this other reactant, right? If we think about it being oxidized, it must have lost electrons. And the way I always remember that, like I said in the previous video, is Leah the lion goes grr. Loss of electrons is oxidized, right? So this is the key feature here, is an oxidizing agent oxidizes something else in the reaction, all right? So then this brings me to my next point. All right, if we lost these electrons, where do they go? Well, they must go to the oxidizing agent, right? If the oxidizing agent is causing this to happen and the other reactant is losing electrons, then that means the oxidizing agent must be receiving those electrons. All right, so let's just write this down. So an oxidizing agent, gains electrons from whatever is being oxidized. All right, so this is kind of the weird paradox, my last bullet point. If the oxidizing agent is gaining electrons, what does that mean is happening? Well, it means if we're gaining electrons, it must be reduced in the process. So therefore, the oxidizing agent gets, I can't write very well today, gets reduced in this process. And this used to always throw me off as a student, where I was like, shouldn't an oxidizing agent get oxidized? No, it's oxidizing something else. Therefore, it's getting reduced. So it's kind of the flip-flop of that. All right, we could do the same thing with the reducing agent. And a reducing agent, like I said, is going to get oxidized in the process. So we'll just say reduces something else. And the reducing agent gets oxidized in this process. All right, I did want to also really drill in one important thing. An oxidizing or reducing agent is an entire reactant, not just an atom. All right, and we'll go over this with our practice, but this is something that always throws people off, is we have to think about the entire reactant as being an oxidizing agent or a reducing agent. We don't just cherry pick one atom out of it. So let's go ahead and take some examples. And we're just going to break these down slowly and go through a handful of these. So let's say we've got SNO, that's tin oxide. And this is a solid, so I'll indicate an S there. and we're going to combine this with hydrogen gas, which is H2. And we're going to go ahead and make elemental tin, which is SN. And we're going to make water. Water is a liquid, tin is a solid. And before I work on these, I always double check that things are balanced. So I've got one tin here, one tin here. That's good. Then I go to oxygen. One oxygen, one oxygen. That's good. Then I go to hydrogen. I've got two hydrogens, two hydrogens. That's good. So it looks like we don't need any reaction coefficients in this case, but it's always a good idea to check. All right, and I'm going to spread this down a little bit. And what I want to do first is assign oxidation numbers. So let's do our tin. Well, over here, I'd say, well, tin, if we look at the periodic table, is kind of near the middle, which means that it's a little hard to identify. So I'm just going to put a question mark here. And then oxygen. We'll go over here. Oxygen, we said, is in group 6A, which means it's always going to be -2. There are some exceptions to this, specifically in peroxides, where it's -1. But for the most part, oxygen is going to be -2. So it's 2 negative, right? Which means we can infer that the tin must be 2 positive, right? In order to cancel things out. So I'll go ahead and just change this to 2 positive. All right, so we've got that reagent taken care of. Next, we'll go to our hydrogen. And this hydrogen right here is elemental, right? It's just hydrogen. So I'm just going to write this as H0, right? So that little 0 superscript is just saying that the charge here, or the oxidation number, is going to be 0. This is how I like doing it. All right, so let's go to the right-hand side. On this side, now tin is by itself, which means that tin must be 0. So I'm just going to put a little 0 there as its oxidation number. And then if I go to hydrogen, this hydrogen is no longer elemental, right? And because it's not elemental, we're going to treat it as an ion. So in this case, it's just going to be H+. All right, so not too bad. And then oxygen, like we said, is going to be treated as ionic. It's group 6A. It's not elemental, so we're just going to treat this as oxygen 2 negative. All right, so we've done all of the hard work here. Now we need to start looking at what's going on. So let's focus on oxygen at first. So oxygen in this process had no loss or gain of electrons, right? It went from an oxidation number of 2- to 2-. So no transfer of electrons going on there. All right, now let's go to tin. Over here, we went from tin 2+ to tin 0. So the question is, how did we go from something that was positive to something that was neutral? Well, we must have gained negative things in order to cancel out the positives, right? So in this case, we must have gained 2 electrons, right? And if we think about gaining 2 electrons, well, we'd say, well, that means that tin was reduced, right? Leo the lion goes grr tells us that, right? And then we'll go and look at our hydrogen. So in hydrogen, oops, that's not a good arrow. I'll just go ahead and say, okay, in this case, we're going from something that was neutral to something that was positive. So we must have lost 1 electron per hydrogen, right? In this case, right, each hydrogen, because we have 2 of them, lost 1 electron. Okay, and that tells us that hydrogen was reduced. Okay, so this is kind of the important thing we're getting out of this part. So I'm just going to make a little table underneath, and I'm just going to say tin gained electrons, therefore it was reduced, and hydrogen lost electrons, therefore it was oxidized. So this is just going to be my little summary underneath. Okay, so let's go back up and try to identify our oxidizing agents and reducing agents. And like I said, it's confusing because they're essentially flip-flopped, right? The oxidizing agent is the reagent that gained electrons during the reaction. So which reagent gained electrons? Well, I would say that the tin oxide gained electrons, right? Because we say right here that it gained electrons in this process. So I'm just going to zoom out a little bit, and I'm just going to do a crossbar, and we'll write our second table over on this side. So that means that the tin oxide was the oxidizing agent in this case because it's the reactant that gained electrons. All right, if we look at what lost electrons, well, I'd say this tells us that the hydrogen lost electrons, specifically H2. So I'm going to go ahead and just write H2 was the reducing agent. All right, so like I said, these are individual atoms. These are entire reactants. All right, let's try to do one more because I know students tend to get a little bit overwhelmed with this, and practice is key. Whoops. All right, so let's do this next example. And in this next example, we're going to do a harder one. We'll do V2O5. I'm just going to keep the states off right now just to keep things simple. We're going to combine this with hydrogen gas, and we're going to make V2O3 plus water. First things first, we always want to make sure things are balanced. I've got 2 vanadium atoms on either side, so I'm good there. I've got 5 oxygens here. I've got 3 here and 1 here. That doesn't look very good. But what if I double my water over here? That means I would have 3, 4, 5 on the right and 5 on the left. So now things look balanced to me. Okay, and then last but not least, I'd look at my my hydrogen. I've got 2 hydrogens, but over here I have 4. That's okay though, because I can go ahead and put a 2 in front of there. So it is a lot of guessing and checking when you're balancing, but make sure you double check everything. Okay, so just like we did before, I'd say oxygen is 2 negative, all right? And if we think about that, 2 negative times 5 atoms is going to be equal to a sum of 10 negative, right? All right, so let's do the other half. We don't know what vanadium is because, again, it's in the central part of the periodic table, but we have 2 atoms, and we know that each of those 2 atoms must add up to cancel out the 10 negative. So this tells me that we've got to be dealing with vanadium 5 plus, right? Because if we've got 5 plus times 2 atoms, we'd be getting a 10 plus, and that means that these 2 would cancel out, which is what we need to have happen with a neutral molecule. So I'm just going to erase this just to keep things neat and tidy. All right, and then over here, we'd say that hydrogen is elemental. It's by itself, so it's H0. Let's do the same thing on this side. We said that oxygen is always 2 negative because it's in group 6A. Over here, we could say, well, 2 negative times 3 atoms is going to be 6 negative, right? And then that means when we're looking at vanadium here, we could say, well, it needs to cancel out the 6 negative, which means it must be 3 positive, right? Because 3 positive times 2 atoms equals 6 positive. And we need to ensure that these values cancel out. So I'll go ahead and erase all of this. All right, and then we'll go over here. We'll say that hydrogen is now in a molecule. So it's going to be hydrogen plus. Oxygen over here is going to be O2 negative because it's always in group 2A. So let's take a look here. For oxygen, for each of these transitions stayed to negative, so no change. All right, so if we want to, we can even just ignore these and just get rid of this. And let's focus now on the hydrogen. And I'll go ahead and take a look here. Well, hydrogen in this case looks like it became more positive. That means it must have lost an electron. Therefore, it must have been oxidized. Right? Now let's do vanadium. Over here, it looks like it went from being really positive to less positive. That means it must have gained electrons. Therefore, this must have been reduced. All right, so let's again make that little table that we did before. So in this case, I'd say hydrogen, lost electrons. Let me just do E minus. Therefore, it was oxidized. We said that vanadium gained electrons. Therefore, it's reduced. However, let's think about the other half of this, right? What was the oxidizing agent? What was the thing that gained electrons? Well, in that case, it'd be V2O5 is the oxidizing agent. So remember, the vanadium is an individual atom where this needs to be the full reagent, and we're going to flip the terms here. So rather than saying reducing agent, it's going to be the oxidizing agent. Then if we go to the next one, we'd say, well, what was the reducing agent? Well, H2, the entire molecule, not just the atom, is the reducing agent. All right, I hope that makes sense, but let me know if you have any questions. I'm always happy to help. Good luck studying.